Hey everybody. I'm just gonna wait a second. There's five here, five. Now we have six. Let me just give everyone a minute, I think. Seven. Okay, let me just give everyone up. Eight. Okay, so we're doing pretty good. I feel like once we have eight, we get started. And now we got all 10. Okay, that's pretty good for 9:31. I like that. Okay, everybody. Good to see you. Now, today now that we've gotten a lot of the fundamentals down about like definitions and certain things, what you can do, what sorts of questions you can answer uh, about integers, basically, we start getting into some of the applications of these things. And today is, I mentioned every number theory textbook has like, or a lot of number theory textbooks don't have as much overlap as someone would figure in the way that other math books on uh, other math topics have. But one of those things that's in every single one of those things that's in every single number theory book is something called the Chinese remainder theorem. And it's called the Chinese remainder theorem because these sorts of questions were first found in Chinese math books. And before getting into, I have a lot of little stuff to do, but I just want to mention just what this is. A Chinese remainder theorem is a question that has this form. Basically, we're looking for a number, and what we're told is, and they didn't say it this way back in the day, but now that we have terminology notation, it's easier to state the problems. To find a single number, when you divide a number by different other numbers, generally you get different remainders. So here's like the classic Chinese remainder theorem problem. To find one number, not three different numbers. Now, with the way they would have said it, they they might say there's a certain number of people, and if I line them up in groups of two, in groups of three, there's one line with two people left over. But if I line them up in groups of five, there's three people that are don't fill up a row. And if I line them up in groups of seven, there's two people that don't fill up a row. But nowadays, we can say that without all the words by saying find a single number x that if you divide it by three, you get remainder two. Take the same number and divide by 5 and get remainder 3, and take the same number and divide by 7, you get remainder 2. What if I told you this number is between 9 and 50? Now, of course, we're going to learn a whole method for solving these, but just for fun, can you use some logic, like a brain teaser, to identify which integer has the property that if I divide by 3, it's remainder 2. If I divide by 5, it's remainder 3. And if I divide by 7, don't type it into the chat yet. Give everyone a second to like mess around with that with this question. I hear what Edward's saying. If you like kind of make a list of all the numbers and sort of start crossing out the like Sherlock Holmes when you cross it when you eliminate everything that's impossible, all that's left is what's possible. Mm-hmm. Yeah, there's different logic you can you can use for this. I mean, I feel like this here is the most useful. That really narrows you down. Anyone want to type in what is it about that middle one that I find most? Uh, I find that like the most useful. Like I feel like that middle one narrows things down a lot. How so? You could type it in to the chat. How does that middle condition? Uh, how does that middle condition get me reduce the possible numbers to very few? And yes, when you divide by 5, either the only way to get remainder 3 is if either you end in if you end in 3, because if you divide something by 10, and uh, because 5 is a factor of 10, um, 13 is a possible answer, 18 is a possible answer, 23 is a possible answer, 28 is a possible answer, 33 is a possible answer, 38 is a possible answer, 43 is a possible answer, and 48. So now we're down from this middle condition. We're down to 1, 2, 3, 4, 5, 6, 7, 8. Now at this point, if you think through the multiples of if you think through the multiples of 7, that really narrows us down also, because the multiples of 7 are 7, 14, 21, 28, 35, 42, 49. And if I want to get remainder 2, I add 2 to each of those. So it becomes 9, 16, 23. And yes, 23 is the answer to this question. And I show that to you because that actually was the actual question from uh, something called, I think it's called Master Son's Mathematical Manual, and I think it was from the year around the year 300 is when this was in a Chinese document. Now, again, this could have been phrased as a word problem, like I have a certain number of soldiers, and when I line them up in groups of 3, somehow I end up with 2 people left over. But if I take the same group of soldiers and line them up in groups of 5, we end up with a row that only has 3 people in it. And if I line them up in groups of 7, I end up with a row. That's how they sometimes word this. You might say, well, that's kind of a weird. Is this just a recreational problem, or is that something of importance? Well, there is actually a practical application to questions of this sort, because back in the day, astronomy was one of the main scientific fields and mathematical fields. And in astronomy, uh, celestial objects uh, reappear every certain number of days. So if there was some situation, where we have the Earth and we have the Moon and we have Jupiter, and they're lined up or something like that, and we want to know, when is the next time, that I'll have, the Moon over here and Jupiter, over here. And that has something to do with like, okay, the moon's going to go around a certain number of times, but then it's going to go more. That's kind of like the remainder. And Jupiter's going to go around and have, if it's over here, it's like a remainder. So it did have like practical application. This is the first mention of the entire course that this numbered theory could have any practical application aside from just riddles. So I just wanted to mention that. Now, this question was at least possible to do through some kind of, sleuthing. But if I were to change the numbers to be bigger, uh, where's my Where's my example? Well, I lost it. That's all right. If I change the question to be, remainder 5 mod 41 and remainder 7 mod 93 and 3 mod 107, well, suddenly we'd be in trouble because that could be a really large number, and I'm not going to be able to use that much logic. Oh, Stephanie, I saw a hand. I just happen to luckily have a view that I can see that. Otherwise, I would. Stephanie, were you raising your hand to answer a question, or did you have a question?
Yeah, no, I wasn't gonna answer anything. If you go back a slide, I'm just missing something. Like it's just not computing.
Oh, do
Like,
you mean why is the answer 23 or
yeah, like 23 equals 3 times or 5 times 5, like
oh,
20.
verifying the answer? Okay, so let's take
Yeah,
a look. So to verify that the answer is correct, which is important because it goes into what the question's asking. They're saying if I take 23 and divide by 3, I get 7 remainder 2, and that's where that 2 is. It doesn't care at all about that number. But if I take 23 and divide by 5, I get 4 remainder 3. So the remainder is what we hoped it would be. And if I take 23
4
and divide
remainder
by
3, but
7,
the 5 goes into, oh, I'm doing the wrong way.
okay, so
21
you were
remainder.
dividing by the 2 or something and just hoping to get
I
3
was
as a
going
remainder?
up. I was going 5 into like 25 to then subtract 20. I don't know. I don't want to confuse anyone what I was doing, but that cleared it up. Thank you.
Okay, yes. So definitely, yeah, being able to verify that the answer is right, hell is like a is demonstrating, yeah, like understanding, making real clear we have what the question's asking. Because I could imagine a question where like this number didn't represent the remainder, but it somehow represented the quotient. Like these numbers, the 7, 4, and 3, those don't matter at all in this question. Just
Yeah.
just the remainder.
Yeah. So it's the whatever five times what is it's going to be less than the number. So that's what I was doing wrong. Okay. Sorry.
Five. Wait, no, no. 5 times is going to be bigger than the 5 times whatever is going to be bigger than the number because it's going to be a remainder.
Yeah, so we have to go under 1. I was going over. I don't know
Uh,
why.
so you're talking about, let's just use this yellow guy. So you were thinking that 28 might be a possible answer? Wait, now I got myself confused.
No, no, I was doing like X would be 25.
Minus 3?
I was subtracting the wrong 2 numbers.
Were you
So I
thinking
don't
maybe
want to confuse anyone else. Like I was doing
okay.
25 minus 23 would give me a remainder of 2, but it's the
I
wrong
see it.
way around.
I understand now.
I don't know
I
why I
got you.
was doing that.
You're using the other mod definition where it's like you subtract the thing. So it would be
Yeah.
23 minus 3 is 20, which is divisible by 5
Yes, that's better.
instead of the remainder way. You know,
Yes.
the remainder way is a good way to think about it. But what I said yesterday with subtraction and is it divisible by 5, that actually is important for a lot of the proofs that we're going to do, that the other way. So I'm glad you're thinking
Yeah.
of it in
Okay.
that other way also. Let me throw the homework answers up. I do like to, people really are doing a nice job on the homework.
Yeah, so whatever I was just doing in my head is why I couldn't do the chart problem.
Okay, and that, okay,
I
so
I followed the pattern for what I could, but I was remembering class incorrectly in my mind.
yeah, to me, it sounds like we have two alternate ways to think about what that triple equal sign means with the mod, and the one where you think about, oh, what's the remainder after I divide, is usually uh, that's usually the more intuitive way to think about it.
Yeah.
But the other way is actually very important. Almost every proof relies on the other way.
Okay.
Hmm.
Thank you.
Okay, let's take a look. Homework. Here we go. As I was saying, the about half the people seem to get the homework done. Uh, I'm going to say by like 6 p.m. something like that. Uh, some people have jobs and different things they're doing. They're not able to do it until later at night. So it's not bad if you don't get it done, by 6 p.m. But I do like to kind of look throughout the day and just see, oh, good, you know. And then the people who get it done earlier, I can usually give some more feedback to. But definitely, I didn't check if they're all in. Um, but people are doing a nice job on the homework assignment. I see pretty good effort on that. These assignments, I hope you appreciate also. Just the right, these are just the right number of questions, level of difficulty. They give you a really good feel for what you expect to see on the final exam. So number one, we basically just multiplied the two answers by 4 to get the two new answers. And number two, we subtracted 17 from the 8 and added 32 to the 15 to get another pair of answers. 3 was just trial and error. I just wanted to just see, do you have a good feel for like messing around, verifying that an answer is correct? Number 4, regardless of which way you did it, if you said, oh, I'm looking for another number that gives remainder 5 when I divide by 6, that's one way. Or if you were looking, what number when I do 65 minus it is the answer a multiple of 6? Either way, you get 65 as the answer for that one. Number 5 was just the definition. So knowing that divide by 9 and get the remainder. I feel like Stephanie maybe was trying to divide by 5 and get remainder 9, maybe. Number 6, 14, 25, and 36. Number 7, this was trial and error. The only method we had for a question like number 7 at this point was trial and error. Uh, Number 8, that one, I hope you found use of that chart maker. We got 5 and 14 for the answer. Number 8, we didn't have to change the answer because the y became negative. But for number 9, the y didn't become negative, so we had to subtract 59 from it and add 18 to the x to get 11 and 36. And then for number 10, some of these were impossible. Like no matter what you do, you multiply 2 and divide by 8, and you're not going to get remainder 1. 4 and 6. A lot of people noticed if the number, like the 2 and the mod number, have a common factor, they're not so-called relatively prime, then there's not going to be an answer for this question. So 2 had no chance, 4 had no chance. 6, even though 6 is not a factor of 8, 6 and 8 have a common factor of 2. So if that happens, there's not going to be an answer. But 3, 5, and 7, actually, it's funny. 3, 5, and 7 became 3, 5, and 7, which is actually kind of unusual. When it was 9, 3 and 6 and oh, I have an error here. Yeah, it says 8 and a, but 8 actually is supposed to be 8. I made a mistake in my chart. And 2 became 5 because 2 times 5 is 10. And notice how 5 then had to become 2. So they kind of come in pairs. 5 times 2 is 10, 2 times 5 is 10. Same thing with 4. 4 times 7 is 28. But on the other hand, 7 times 4 is 28. So they kind of come in pairs, except the 8, it was 8 times itself. 8 times 8 is 64, which is one more than 63. So that was the homework.
Do you mind going back to number 9?
Mm-hmm. So for number 9,
Flew by it. I did it like 80,000 times and I still don't understand what you did on the last step.
Let me pull up that chart maker thing.
By the way, I couldn't copy your chart maker, so I actually just decided to do my own and put formulas in the cells. Did anyone else
Oh,
cut and
did
paste
your
it?
own. I'll tell you, it was hard for me to do that one because it's like recursive, but you did it and it worked. Because
Yeah, I
you
didn't
would have
copy
to
them
know
from
what
cell to
number
cell.
to
I
multiply
literally
by.
did cell by cell by cell. Like, yeah, I didn't copy well, I guess I did end up using dollar signs. It doesn't matter. Yeah, I did my own, but I couldn't cut and paste.
Oh, I wasn't thinking cut and paste. You just say, you open it and then you say save, and then you save your own copy, which you can
Oh,
then.
okay, now I feel like an idiot. Yeah, I didn't try.
No, you shouldn't, because if that's not a thing that you had ever done before. But yeah, you could just sort of like save your own copy, and then you can edit. You can edit your own copy.
Yeah, but
Um,
using it made me realize the day when we were doing this over and over again, I wish I'd done that, just
you wish you had done what?
created a table with formulas, because I sat there, go up two, minus that, multiply, go up two,
Oh yeah,
know,
yeah. With a
and
dollar
I'm
sign, like
writing it all out on the side to make sure I don't make mistakes. But yeah,
yes,
so not the 959x minus 18y. That's this one, right?
yeah, 59x. So I did 59x plus 18y, and here's the chart.
Yeah, so I got
Now
to
my
-7 and 23, and I just called it a day. Like,
yes. So the problem with -7 and 23 is that that would be good if it was 18x minus 59y, but it was 59x minus 18y.
oh, yeah.
That was the issue. So we really wanted the y value to be negative. So that was the issue. So I had to take these two numbers, the -7 and 23, and I had to create the alternate answer, the answer where the x is positive and the y is negative. So I added 18 to x because it's 18y, and I subtracted 59 from 23,
Oh, okay, the other thing that we did. Okay,
and that's where the 11 and 36 came from.
okay. Thank you. Sorry.
No, that's all right. Listen, you guys should all know that asking questions, uh, I am, I'm not in any rush. I have a list. I made a very ambitious list on the before the course started, of uh, about 20 topics I could feasibly do, and we've we're easily going to cover the most essential of those, and it's fine with me if we go at a pace where people can ask questions, and then maybe we don't get to some obscure topic that I was maybe going to do. It's totally fine. Okay, now let me get my notes here to okay, so my notes have become uh, unorganized, and I'm sorry about that. Let me. Oh, and the chart. I've now given you a copy of the fully filled out chart. So let's just take a look at that. In where it says class class 6, day 6, in there is a oh, there's a couple of cool things. First of all, there's the chart. Well, that's no good. Is the chart totally filled out? Okay, so I gave you the wrong chart. Does that mean that this is wrong also? Hold on. No, that one is totally filled out. I'm going to update this to give you the proper chart. Hold on. Let me do that now so that you can bring that up. So even though for homework I only had you do 2 of the columns, uh, here is the complete chart. Let me give it to you. Okay, that should be good. Okay, this should be better. Screenshot. Let's see. That's the bad one again. I'll have to delete that one. Instead, this new one. Okay, so as you can see, the entire chart is filled out for you now. And if you like, I think it's worthwhile you look at it and say, huh, I don't believe one of these. So let me try it out. 4 in the fourth row times 10 is 40. And 40 is one more than 39, which is a multiple of 13. That's why 10 is the right answer, because 4 times 10 mod 13 is 1. 5 times 8 is also 40. So 5 times 8 divided by 13 is remainder 1. 6 times 11 is 66. 13 times 5 is 65. So it is true. So it's fun to look at these because a couple of things to notice. One is the way the numbers like happen in pairs. Like if 2 is 4, 4 is 2. And how about this kind of last one's kind of 11 and 13 were prime numbers. And because they're prime, they were no illegal values because in none of these rows was something have a common factor. And you can also see what's kind of cool about the prime numbers 7, 5, 11, 13 is that all the numbers are different. Basically, they come in pairs, and like 2 goes with 6 and 6 goes with 2, but every single number gets represented, and that's kind of neat. Every number has like a unique answer. There's no repeats in column 11. There's no repeats in column 13. All numbers from 2 to from 2. There's no, oh, of course over here. I probably should have made my rows go up to 12 or up to 13 or something. I didn't. Now that I look at that, this would make more sense if I had 3 more rows, but I didn't want to make it so hard to do. Now, is there some way to do this without trial and error? Is there some way I could have known that 9 or that, let's say, that 6 was going to have an 11? Whoops. There's some way to have known that. So that's what I want to show you first today. Is there a way to answer questions like 6x is congruent to 1 mod 13 that does not involve guess and check? Well, by the way, this is also we also could say this question as what is 6 with a little -1? That just means what's called the modular inverse. Mod 13. That's the same question. And we know the answer is 11. Well, one really fun way to get the inverse is to use a calculator that's designed for it. So check this out. I have provided this for you because sometimes we don't need to go once we demonstrate that we know how to find the inverse, we don't actually have to keep doing it. So check it out. You like this for a given for given coprime numbers a and n. So I just say 6 is the sort of number and 13 is the mod. And I click submit and I hope it says 11 and it does. It says it down here. 6 times 11 is equal to 1. See, inverse is 2 numbers that when you multiply together, you get 1. It's kind of like reciprocal, although in this type of math, there's no fractions. So this is kind of fun because now I could go crazy, what's, 101, and it will tell me that 9 times 45 would be 1 mod 101. Oh, I said 45. Of course, that's going to come 9. 47 times 43 These are, so we have a calculator for it. But is there some way that, how does the calculator do it? And here's where something fun is going to happen, I think at least. Now, Edward, did you notice this yesterday? How can we
No,
do
not
this
hard.
utilizing something else we learned yesterday?
We
And give you
can
reasoning.
we can use Euclid's algorithm. The setup here is that 6x minus 13y minus some multiple of 13 is going to be equal to 1, and that's
That's
going
right.
to give us
Okay, wait, let's stop there. Edward says that these two questions are somehow related to each other. And this is very good. Check it out. I'm going to do something kind of funny here. 6x divided by 13 is something. Can I just call it q? This class likes variables better than most classes, although they like them when they're written nicely. I'll say q. So that makes this, oh, well, you know what? Why don't I not call it q? I think we'll all appreciate if it's called y for now. So that makes this 13y. Then when you subtract, you get remainder 6x minus 13y. But we want that to be 1. Or I kind of like what Edward said about how 6x is 1 more than some multiple of 13. So if I subtract it, if I subtract some multiple of 13, whoops, I should get 1. You could even say, remember from yesterday, the definition of mod is that 6x minus 1 should be divisible by 13. So it's 13y. And then if I rearrange it, I get 6x minus 13y equals 1. No matter how you think about it, the question we learned yesterday in the beginning of class answers the question we learned how to do by trial and error at the end of class. Now, even if you're not understanding exactly, like why am I allowed to rearrange it? Can we just say, just do it, rearrange it. If you see, put the 6x here, put the 1 here, put the minus, put the 13 there, and throw a y there. So if I say, oh, I want to know 8x is congruent to 1 mod 17, I'm going to change it to 8x minus 17y equals 1. I do want you to be able to convert from one form to the other. And you might be confused, like, why am I doing that? It's because when something's remainder 1, it means that it's 1 bigger than a multiple of it, which means if I subtract the multiple of it from it, I'll get the number 1.
Can you say that one more time?
Not only will I say it one more time, I'm going to actually put an example. I'm sorry, let me pick a better. Let's say 7 times 4. Okay. So Stephanie, would you agree that this is true?
I'm having trouble with these. Like, I don't know why.
Well,
My 7 times.
what if I do 7 times 4? Would you agree that this is true? How would you verify whether or not that's true?
So a multiple of 9.
Well, what about just by dividing? what division could you do to verify whether this thing is true?
Yeah, this part is losing me. I'm not gonna lie.
Okay, I think the easiest way is just
Would you
divide 28
divide
by
20
9.
by 9? Am I
Yeah.
on the right track? Divide 28 by 9, which would be 27, and then you have the plus 1.
Okay.
That's right. I think that's probably the best way to think about this. Think about the 1. We hope it's the remainder when you divide 28 by 9, which it is, because 28 divided by 9 is 3, remainder 1. So this is more like the notation. I'm sure, Stephanie, if I just ask the question, is it
Yes,
true?
exactly. That's what the notation is losing me. That's it.
Yeah, that's what this notation. And it might be, I might have confused people yesterday by saying there's an alternate way to verify it, which is to do 28 minus 1 and see if that's a multiple of 9, which is true. But probably easiest to think of it this way. So, and this would make sense why you've struggled with the chart. So, Stephanie, just to throw one more sort of question like that,
Okay.
is it true or false that 30 is equal to 2 mod 7? So that might be false. It might be true. Which do you think it is? So I'll stick with Stephanie on that.
Yes. True.
Why do you think that's true?
Because 30 minus 28 is 2.
Okay. Yes, and yes. So you do it with subtraction. Are you also thinking of division? Is that because that was the step?
28, yeah, 28 is the closest multiple of
Yes,
7.
yes, right. That's right.
Okay.
So now let's come back over here.
Thank you. No, that really did help me. Sorry.
I have a little more. I got a little more to say about this here now. Now that we've established that 7 times 4, whoops, does that work? No. Oh, probably shouldn't erase this because now when I upload the notes, they're not there, but I'm too far. Now, it's also true. This is true. It's also true that 28 minus 3 times 9 does equal 1. Right? I said that's definitely true. That also is a way of saying it's remainder 1. When I subtract away, like you said, Stephanie, the biggest multiple, like the closest thing to it. So 28 minus 3 times 9 equals 1. That's going to be true. So when I say something like 7x is congruent to 1 mod 9, that means that 7x minus the closest multiple. Now we don't know what x is. So we don't know what the closest multiple is, but it's 9 times something. And it should equal 1. And that's a little explanation of why you were always allowed to convert an equation that looks like this into an equation that looks like that. So if I say 6x is congruent to 1 mod 11, what would be the equation? The equation that would have a regular equals 1 here and a minus there. I'll go for let's have someone raise a hand just to just say what the new question is going to be. That is equivalent. Okay, Aveline?
Is it 6x minus 11y is equal to 1?
That's right. Whoops, 6x minus 11.
I don't want
Now,
to kick dirt into this, but what can you do what if the remainder is 2? Does that follow, or is that blow it out of the water because you can't use the Euclidean thing anymore?
okay, you can use the Euclidean thing for other numbers. Yesterday we started by getting other numbers by either getting down to 1 and then multiplying by those other numbers. Like if you look at question 1 from the homework, it was a different number. So we could get, but honestly, equals 1 is the most important one to get.
Oh, okay.
So we're going to be pretty much always doing equals 1. Equals 1's got a special importance to it.
Okay.
Now, if you're wondering, like, whoops, And now, yesterday, and I have an example here just to like drive the point home. Hold on. I'm really annoyed with myself because I didn't leave myself enough pages in my notebook to to put my notes for today, and I lost. Where did I? Where did? So I went to like a back page, and now I've lost it. Oh, here it is. So check out a really hard question, which is this. 53x is congruent to 1 mod 193. That's a very hard question. But if I convert it into this question, well, it's still pretty annoying. But yesterday we learned how to do questions like this. In fact, questions 8 and 9 yesterday were about doing questions like this. We would end up with minus 14 and 51. However, no, we would not be done because I was hoping that the 51 would be, I was hoping, get those guys out of it. I was hoping the 51 would be negative. So what do I do to adjust my answers? Because I don't want 51 to be positive because then I want the 51, sorry. Guess what? Good news, everybody. I got myself confused, but I actually am happy. How did I turn from sad to happy so quickly? Anyone know? I don't need to adjust, even though the 51 is positive. Does anyone know why? I thought I needed to do the other answer, but I don't. Hand to volunteer for that. Why am I actually pretty happy now?
Professor, I have a question because
Yes.
I don't know why 193 as x,
Oh.
not y. Is it not supposed to be 53x minus 1?
Oh, thank you. Thank you. That should be why. Thank you very much. Thank you. That was supposed to be why. And so here I am at the answer. It's actually minus 1451. And I'm happy. I'm actually not going to do that adjustment factor. Anyone know why not?
Well, I guess you wanted x to be negative.
Well, I didn't want x to be negative. I wanted y to be negative, but it was because the 193 this was in the 193 column. It's not necessarily that I wanted x or y to be negative, but I wanted the thing with the 193 to be negative. And since it was, I'm done because this means 53 times 51 minus I'm sorry, I should say, yeah, 53 times 51 minus 14 times 193 equals 1, which means 51 is actually the answer to the question. X equals 51.
So to switch those from positive to negative, we would do 14 plus 53.
Negative 14 plus 53, yes?
Yeah, and then 51 minus 193.
That's right.
Right. Okay.
Now check it out. So I say that the process we learned yesterday will answer this question now, as long as you know how to turn it into this question and how to follow through with it. And just to verify, here I come over here to the online modular inverse calculator, my trusted friend, and I put 53 here, and I put 193 here, and I hope it says 51, and yes, it did. So online modular inverse calculator, you actually can use that. You see, on a final exam, I would probably never have you go through an entire process for this. I would probably have you do, there would be a question like, I could ask 53x minus 193y equals 1. Yes, that's from class 4, class 5, I mean. That's a final exam type question. Another final exam type question would be, to solve 53x is congruent to 1 mod 193, I can do ax minus by equals c. You know, what are a, b, and c? And you would say 53 minus 193y. And then you would end there. That's how I make tests. It's like, okay, yes, of course you could get all the way from here all the way to the answer, but I'm happy if you prove to me you can get from here to here, and you separately prove to me that you could get from here to the answer. To me, you've learned, the math. Whether we do it all in one question isn't that important. Whether it's like all strung together.
Professor, could
Yeah.
you go back to page 11, the previous page?
This one, yeah.
So I was doing what Stephanie suggested with the negative 14 and then the positive 51, and you're like, oh, 51's not negative. Before you
Yeah.
had your little eureka, we would have subtracted 193 from the 51. We
Yes.
would have added 53 to the 14.
Are you wondering what would that give us?
Yes. I mean, I can do it, but it wasn't what you said. Unless I
Yeah,
did something
because
wrong.
that's if the question was 193x is congruent to 1 mod 53, which would turn into 193x minus 53y equals 1. See, that question where the 193 and 53 are like switched from this would be the other answer. So one answer answers 53x minus 193y equals 1, where that other answer where you subtracted from the 51 and added to the negative 14 would be if the two things were flip-flopped.
Okay, I'm still kind of in the dark. I don't understand.
Well,
I
remember
do.
in the homework yesterday, question number 3 yesterday, I wanted you to mess around with 3x minus 5y equals 1 versus
Okay,
5x minus 3y equals 1.
yep,
So in this one, I would want the thing in the, if I were making my column like that, if I'm doing this question, I would hope that this number was negative, because like the thing with the, whether we call it X or Y, the thing underneath the, in fact, I kind of regret that
oh, you want the Y to be okay, I got it.
yeah.
I didn't know, okay, I did not notice that.
And if this one, but I do regret constantly saying I want the Y to be negative. It's not necessarily the X or the Y I want to be negative. In this one, I want the thing that's with the 3 to be negative,
The thing that's
whether I'm calling it X or Y.
right, whatever's next to the subtracted side.
Yes.
Yeah.
Yeah, I should have said that.
Professor, I'm also confused on, well, what would you do if it's not negative to make it negative? That step is still confusing me.
Oh, so here I am over here. Like, let's say I wanted this 51 to be negative. Are you saying? Are you saying this 51, if I somehow wanted it to be a negative number?
No, let's say
Or
like, yeah, let's say
how to
you
do
use the
it, or are you
process with any
wondering?
number and you want it to be negative, but it's not. How would you?
Yeah, if it's positive, you subtract this number from it. So
Okay.
go to the top of the other column and subtract that number from it. And if
Okay.
it's negative, you add the number that's at the top of the other column. That will always get you the other answer.
Okay. Thank you.
Okay, so now we are ready. And for the next about 40 minutes, I have some more facts about the triple equal sign. Because even though the triple equal sign looks kind of like an equal sign with a extra line in it, and it is related to a regular equal sign, but there are some things that it has in common with a regular equal sign, and some things it says. Oh, Stephanie, I see a hand.
I guess when we go to break, I wanted to look at that other slide really quick before we moved on, but I guess I can wait.
You're okay to wait?
Yes, sir.
Okay.
Yeah, it's fine.
We'll make time during the break. Now, so here's a couple of things. Let's start with a true congruence. It is true, we'd all agree that 7 is congruent to 2 mod 5. Like that's true. It's also true that 14 is congruent. I know I'm also going to stick with mod 5. Now you might say, oh, obviously you have to put a 4 here, but you don't. You could put, you could put any number that's not, it doesn't have to be the remainder. Very often it is the remainder. But if I put the number 9 here, that's true still. They both give remainder 4 when you divide by 5. So these are both true. Here's my question for you. Do you think it will still be true if I add these together, but keep it as mod 5? Is it true in this case? Is it true in this case? And do you think it's like always true? Like if I add things in that way, is it always true that you can just basically add, let's say mod M, C is congruent to D mod M? Do you think we could just also say it's definitely also true?
So where does the 9 come from? Mod 5 would be a multiple of 5 would be 10. 14 minus 10 is 4.
Well, yes, it also is congruent to 4, but this congruent symbol doesn't have to mean what's the remainder. It just has to mean that the two numbers have the same remainder. So 14 has a remainder 4 when you divide by 5, and so does 9.
Oh, I didn't know that.
Very often, Stephanie, I make the number on the right side of the triple equal sign less than the mod number, so then it would be the remainder. But this is also true.
So if it was 5 times 1, then it would be 14 minus 5 is 9.
Yeah, I guess you could just subtract away. That's right. You could subtract away fewer 5s. That's right.
Okay.
But my question is it true in this case? Is it true that 21 is congruent to 11 mod 5? Let's start with that. You can type it into the chat. So
But that the number before the mod is not always the remainder. It's a number that like
Is left over.
the same remainder as
same remainder.
the one. Okay.
That's right. That's right. But most of the time, Stephanie, usually we make it the remainder.
Okay.
But that doesn't mean that 14 is not congruent to 9 mod 5. As long as the two numbers would get the same remainder, it counts.
So is there a word, like is there a name for what the 7 is before the congruent? And then a name for the 2? Like if we looked at the first example.
Uh-huh. Well, I'll tell you that. When the thing on the right, like in the top one, when the thing on the right is smaller than this number, there is a name for that. They call it, it's a fancy name, they call it the least residue. But there's no special name for the things on the two sides, like the 7, like the 14 and the 9. It's just the left side and the right side of the congruence.
Okay.
Now, Stephanie, since we're sort of getting you up to speed on this, is this true though? Is 21 congruent to 11 mod 5? Is that a true statement or a false one?
True.
Why do you say that?
Well, because 21 minus 10 is 11.
Oh, 21 minus 11 is 10. Or 21 minus 10 is 11. That's right. So you're kind of using a hybrid of the
I don't know. That's how my brain is doing it, but I can't
Right.
take notes on this because I don't even know what to write.
Anyone have another way of saying why do we know 21 is congruent to 11? What's maybe something that uses the word remainder?
Yeah,
So
because
I
21.
Yeah, Genoa?
Can I
Why do
go
you
on?
say?
When you divide 5 into 21 and 11, there's a remainder of 1. So 21 would be 4 remainder 1, and then 11 would be 2 remainder 1.
That's right. Now, Stephanie, what you said about 21 minus 2 times 5, that does work. That is true. If you notice that, you could also do 21 minus 11 and notice that it's 5 times 2, which is similar to what you said. But either way, yes, this worked. And good news for you, it is always true. So I'll write it down as a theorem. If A is congruent to B mod M, and it's also true that C is equal to D mod M, I'm telling you that it is true. You are allowed to add both sides. Don't add the M's together. That thing is actually a little hard to prove. I'm actually not going to prove it. I'm just going to do informally. You know, imagine 7 is 2 remainder 5. Sorry, 7 divided by 5 is remainder 2, but 8. Sorry, I want to have, but 6 is 1 mod 5. So when you put them together, the way I see it is the 7 has 2 guys left over and the 6 has 1 guy left over. So the 13 is definitely going to have sort of 3 left over, like the 2 5s with the 3 left over. I'm just going to go informally. Can I just make a note here? This thing, formal proof is annoying. I might, after class, for people who want to stay for a minute, show you what the formal proofs of these sorts of things look like. But it's not part of the course for us. I'm happy for us to like say, okay, that seems like it's definitely true in this case. Definitely true in this case. Seems like it should always be true. But some things that seem like they should always be true are not always true. But in this case, they are. Okay, my next question for you. If 7 is 2 mod 5, do you think that you are allowed, this part's true, do you think it's legal to multiply both sides by a number? So here I tried to multiply both sides of the congruence by something, in this case 3. So is it true in this case? And do you think it's, and is, do you suspect, is it always true? So is it true in this case? And then is it always true? Maybe, Tammy, do you want to say just in this case, did it end up being true in this case? Like I multiplied both sides of the 7 is congruent to 2. Did it end up being true in this case? Like, did I end up with a true statement again, or is that false now?
I believe it is first because 21 divided by 5, I don't think the remainder is going to be 6.
No, it doesn't have to be. As long as when you divide 6 by 5, you get the same remainder as you got when you divided 21 by 5.
Then it's true.
That's right, and it is. Yeah, sometimes when you add them to, when you multiply them together, you end up with something bigger than the mod, but that's okay. So it turns out it is true. It is true in this case. And theorem, if it's true that A is congruent to B for whatever the numbers are, then CA is going to be congruent to CB mod M also. So you are allowed to add, and you're allowed to multiply. And just in case you want to know, you are also allowed to subtract. That would work.
Wait, how did you know to multiply by 3? Was that just
Oh no,
can
no,
it
I
just
couldn't multiply by
number?
anything. I
Any
just
number?
chose that. So let's say this is true, and instead I multiplied both sides by 4.
Mm-hmm.
It became
It would still be
28, and 4 times 2 became 8. And if you check, it works because they both give remainder 3. So no matter what number you put out here, it's going to work.
okay. Thanks. Can you go back to the theorem really quickly, please?
Yeah. Here's the here's the
One.
So with these two theorems, it's going to allow us to kind of like to do algebra, because algebra is when you do stuff to both sides. This rule, by the way, is going to break down with division, but that we'll look at that. Now, check this out. I want to show you something real sneaky now. Okay, so here's a question. And I want to show you how we now have the ability to do this. This is a new question. Okay, not trial and error, not trial and error. But we are allowed to use, we're allowed to cheat a little bit. We are allowed to use this chart. So here, let me grab this chart. Remember this chart that we got now? What's important from this chart is that we want to look up what is the inverse of 5 mod 7. And for that, I can either go here and say, okay, mod 7, 5 has a 3 here. This is just looking at it from the chart, equals 3 from the chart. So as long as our chart has this number as a row and this number as a column, I can look up this number on the chart. Or if I want, I can go to my handy online modular inverse calculator and type 5, 7, and it says 3. Or,
Question.
yes.
So if since we did 5x congruence for mod 7 is equal to 3. So if it was 10x congruence 4, would it be 6?
Oh, no, I haven't answered the question yet. I haven't even used this 4 yet. That's not, I'm saying the first step, no matter what this number is to look at basically the answer if it was a 1.
Okay.
So as long as 5 is the row, 5 is the row and
7 is the column.
okay.
So the question is, how do I use the fact that the answer, well, here it comes. I think you really like this. 5x is congruent to 4. I'm leaving a little space here. You'll see why. Now, if this was regular algebra, and fractions were allowed, what would you do to both sides? Let me get a volunteer for that, like a hand. if this was regular algebra, like there was no mod 7, if the question just said 5x equals 4, and that was the whole question, okay, I see more hands. What would I do? This is, just algebra. If this was like old school, no, we weren't in number theory. We were in like, okay. Okay, Genoa, what would I do
Divide
in this
5
case?
on both sides.
Say it again.
Divide 5 on both sides.
That's right. So I would divide both sides by 5 and get x equals 4/5. What if I say I don't like division? I like multiplication. What if I don't know how to divide, but I'm an expert at multiplying?
The reciprocal.
Yes, you would multiply both sides by the reciprocal. And you would get 1x equals 4/5, same answer. Well, here we go, everyone. Really fun thing about to happen. Because this type of math does not have division in it, it only has multiplication. So from the chart, from the chart, 5 inverse mod 7 is equal to 3. So what I'm going to do, 3 is kind of like, it's kind of like 1/5. It's like the reciprocal, because 5 times 1/5 is 1, but 5 times 3 is 1 in mod 7 world. So the funny thing you do, I'll make a note here. Multiply both sides by 5 inverse mod 7.
Can you say that again, please? What exactly is like 1/5?
What's the 3 is? Because 1/5, 5 times 1/5 is 1 in regular math. But 5 times 3 is 1 in mod 7 math. 5 times 3 is 15. 15 divided by 7 is remainder 1. So 3 is like the reciprocal of 5. It's not the reciprocal because it's not a fraction, but it's like a reciprocal because when you multiply 5 times 3, you get 15. 15 mod 7 is 1. So in a sense, it turns it, 3 times 5 turns into 1. Remember yesterday we were answering this question by trial and error. X equals 1, no. X equals 2, 5x equals 10, no. X equals 3, 5x equals 15, yes. Because 15 divided by 7 is remainder 1. So what we say when this is true, because x equals 3, we say that the inverse of 5 in mod 7 world is equal to 3. That's what we were doing yesterday, finding the inverse. And today I'm showing you we can actually use the inverse. Let's keep going. The 3 times 5, what happens with those? What could I do now? Where does that turn into?
What, 15?
Well, kind of, but better than that,
X?
just x. They cancel out. In the same way that 5 times 1/5, when I do 5x equals 4, and I do 1/5 on both sides, the reason I do that is because 1/5 times 5 is 1. But in this world, 3 times 5 is 1, as weird as that sounds. And the right side becomes 12. Now, I prefer for that 12 to be reduced to the smallest thing that's congruent to it. So you finish out by doing 12 divided by 7 and taking the remainder. I'm going to make this neater on another page and do another example nice and carefully. But the answer to this question is 5. And you can check 5 times 5 is 25. 25 divided by 7 is indeed 3 remainder 4. Remainder 4 like I was hoping. Let me do a brand new one totally from scratch. 7x, I'm going to do this nice and carefully, is congruent to 3 mod 11. I'm going to multiply. I can't divide both sides by 7, but I can multiply both sides. But what is it you want to multiply both sides by? Hint.
1/7.
It's on this chart. So everyone, take a look at that chart and think to yourself, what do you think should go on both sides? Everyone work on that now. What do you think I should multiply on both sides so that I can cancel out that 7? Everyone think about that.
Can you put the chart back for a second?
Yes. The chart is over here. And the chart, by the way, you have the chart in the Google Classroom, but there's one that's filled in and one that's not. Here's the chart again. So there's a number on this chart that's going to be very useful. Aaron, do you know which number from this chart is going to be most useful in solving this problem?
8.
8. 8 is exactly right. I'm going to make a note here. 7 times 8 is 56, which is 1 mod 11. It was on the chart. 8 was on the chart. Also, for homework, you're totally allowed, especially if the numbers are on the chart, to say 711. Those are your lucky numbers. 711, and it says 8. So what you do with that 8 is you put it here and here. So I'm going to make a note. Multiply.
So how is 56 equal to 1 mod 11?
11 times 5 is 55, which is 1 less than 56.
Okay.
Or said another way, 56 divided by 11 is 5 remainder 1.
Okay. Thank you.
So multiply both sides by 7 inverse mod 11. Because 7 inverse mod 11 is a different number than 7 inverse mod 13 or whatever equals 8. Now, I don't like to have this number be 24. I want it to be less than 11. So do one last step. Do 24 divided by 11, which is 2 remainder 2. And that's the answer. And if you don't believe it, go back to the initial question. 7 times 2 is 14. 14 divided by 11 does have remainder 3.
X is congruent to 2 mod 11 though, right? Or do we drop
Yeah,
it?
yeah. I'm actually turning it into an equal sign for this last step because remember I wanted to have once I get it down to the smallest, the actual remainder, I'm kind of like, because remember the initial question was like had an X here and I just want to know what X equals.
Mm-hmm.
But you are right. X actually is congruent to 2, and any number like 2 works, but 13 would also work, and 25 would also work.
So where'd you get the 14 from?
Oh, The 14? Oh,
Oh,
the
you just
14
did-
came from at the end. I wanted to check my answer. Because
Oh,
the
okay.
question was 7x. So I did 7 times 2. I read if x is 2, then 2 should work in this question, right? 7 times x should equal 3, mod 11. So
Yeah.
I plugged 2 in just to see, is it true that 14 is congruent to 3 mod 11? And yes, it was. Why don't I give you guys one to do in groups just to nail this home? Let's say, let me make sure it's one that's on the chart. Okay, so as long as I have 9, I'll do 9 and 13. So here's for you to do. 9x is congruent to 6. I'm going to pop you into groups to just mess around and talk about this right now. So then we're actually going to take a break before we get to the next topic. Breakout rooms. I will make. I'm going to go to the 4 breakout rooms. That way, it's groups of 2 and 3, 2 groups of 2 and 2 groups of 3. Okay, so I'll see you back here in like 5 minutes.
So the mod 12 for number 9 is NA.
Oh, mod 12. Except it's not 12, it's 13, and the question is with 13.
Oh, okay,
But you're
sorry.
right. If that was a 12, this would be an impossible question.
Oh, I thought
Could you quickly drop a link to the table in the chat? I just lost my table. I don't know where it is.
So the table, yes. Let's see how I do this. I think if I come here and
Oh, it's there in the assignments. I can pick it up there. Okay. I just couldn't remember where it was.
oh, I got you. Yeah, it's in the assignment.
But yeah,
But you know,
you
here it is.
drop it there, that was faster.
You're okay here. Okay, so let me. I'll put it into the chat also, just so that it's there. Let me go. Everyone in meeting. I think this is the proper version of it. See the bottom one. Is that the one that's filled out? Yes.
Yep. Okay, thank you.
Okay, so everyone who's going to work on this question, this is like a key question, and on the final, I would actually give you the chart so you can complete this with
Okay.
the chart. Yeah, it's it. Okay, so here you go. 5-6 minutes in the room. See you soon. Okay, hey everybody. Okay, so the rooms I went into, I only got into 2 of the rooms, but that looked very good from what I saw. The key number was the number 3. It's the modular. There's another place to look for mod inverses in Wolfram Alpha, which is like the king of like graphing calculators. I wonder how I write it. Modular inverse of 9 mod 13. Let me see how it wants me to say it. How would I write it? I'm going to say 9 inverse mod 13. I just want to see what I could type to do it. Yeah. See? Oh, it's not saying the answer. Ha! It's not saying the answer. What if I say 9 to the negative 1 power mod 13? That does it pretty nicely. So mod inverse of 9 mod 13. There's different things you could type where it will know inverse. Here's what they want. Inverse of 9 mod 13. So that's the words you would write. Inverse of 9 mod 13 says 3. Anyway, this one's really good. 9 13. Or you could just say 9 times 3 is 27. 27 is 1 more than 26. Either way, multiply both sides by that 3. This 9 turns into a 1 now, because 3 times 9 mod 13 is 1. And the 18, it's not that the 18 is wrong, but we want to cut this number down to size. So do 18 mod 13 also, and 5 is the answer. And here I did a little check also. I actually went back to the initial question and said, well, 9 times 5 is 45. 45 divided by 13 is 3 remainder 6, which is exactly what I was hoping. Okay, that's a good break point. I think we need a 10-minute break after that, so I'll see everyone at 11:08. Anyone who wants to stick around, I can answer questions.
Professor, can I show you my homework from yesterday? I'm going to figure out my phone situation today.
Okay, hold on. Let me change my view to speaker view. Okay, yes. Okay, I have you nice big on the screen now. Okay, so yes, okay. Good. Keep going. See? Okay. Yes, thank you. Okay, is there another page also? Oh, you froze. Or I froze. Oh, it froze for a sec. And did you filled in the chart also?
Yeah, I filled in the chart. This is the work for filling in the chart. I mean, let me skip it. Let me just show you all the problems instead of the work for filling in the chart. So here's the rest of the problems. And there's one more page here.
Okay, great. Okay, you're in good shape. I'll fix that.
Thank you.
You're welcome.
Professor, can you also grade my chart? You didn't grade my chart.
You fixed the chart?
Yeah, I wrote it out. You didn't grade that part though.
Okay, so I have that. Let me just let me move this off. Okay, let's see. Now, so you understood what the goal of like what made those numbers what they needed to be in the chart, like how you knew when they were right?
Yeah. Can you hear me?
Yeah. I'm looking now. Okay, I see. Yes. So you're doing the trial and error. Yes. Oh, I see. Just writing the numbers. I got you. Okay, good. Okay, so I'm gonna fix that grade.
And remember on Thursday when we went into class, for Wednesday's homework, you had told me that two of those questions you told me it wasn't finished, and then I finished them in class and I showed it to you, but you never
No,
figured.
no, you didn't finish it. You went you divided and got to the next step, but it wasn't finished because it didn't get down to the number one. You never got to remainder one. You stopped when you so just let me bring up the yeah those that was the thing. No, they weren't finished. I'll show you what I mean by that.
I finished them in class, and then you came back and you looked over it.
They you got them down to so it
Oh,
was at
what?
remainder
So I'm
one.
going to, yeah, I'm going to maybe just take a picture and send it to you because I did remember doing that when I was in class.
And did you I see. Yeah, why don't you I want to see what that looks like because from what I remember, you had done 19 different subtractions and I said, "Oh, well you could do it in one step." But that didn't mean that it was done. That one step just skipped. That made it, quicker, but then you had to divide again and keep dividing. So you'll show me that.
Okay, I will. Thank you.
Okay. Okay, everybody, welcome back. Let's see, is everyone here? Let's if you're here, let's see your face. There we go. Okay. Now we are going to learn how to solve. It's gonna take a little bit, but questions of this sort. So this is sort of the goal. To be able to solve questions where we have two equations, and this could even get harder with more equations. I think I might make that a challenge question, optional challenge question. But the goal is to find a single number that if you divide by 11, you get remainder 8. But if you divide the same number by 17, you get remainder 5. And that we have to build up to that question. It's gonna be a while before we revisit that question. There is a situation of Chinese remainder that's easier than other ones. For instance, I suppose if my question was this, if I got really lucky and these two numbers were both zeros, just to build up. Everyone think about that one. So this is our first Chinese remainder theorem question, where the things after the equal sign are both zeros, just to build up from like what's the easiest, like intuitive Chinese remainder theorem question that we could think of. I'll do a cold call. I see Jingyi. Did you know what the answer for this one is? Like just no method, just like by looking at it. Do you know what the answer would have to be?
35.
That's right. So in this very special case, the answer would be, oops, I just, hold on a second. In this one, the answer is 35. So this is, we'd be very lucky if that was the question, but it's true because 5 times 7 is 35. And because 35 is a multiple of both 5 and 7, if I divide 35 by 5, I get 7 remainder 0. And if I divide by 7, I get 5 remainder 0. So let's hope that comes up. That's the easiest of the cases if it just says equals 0. So case 1, we'll say. Case type 1. They both have 0. But it can get harder. What if it's not remainder 0? But what if the remainders are the same? So type 2, same remainder. I like this question. What do you think of that? It's harder. Okay. Edward messaged me. That's right. Anyone have a theory about what the answer might be for this one? Okay. There. Oh, let me see if I could see. You can do the hand raising thing if you want. Anyone have a suspicion about what to do if the remainders, they're not 0, but they're the same number? Everyone in the chat? Anyone want to take a crack at it in the chat? Okay, Lisa says 79 with a question mark, and Jingyi says 79 also, and Edward also said that. So yes, it is 79. 11 times 7 plus 2 is 79. And of course, if I divide by 11, I'll go like that. If I divide by 11, I get 7 remainder 2. But if I divide by 7, I get 11 remainder 2. 11 times 7 has no remainder. So the number 79, or 11 times 7 plus 2, if I divide by 11, this piece has no remainder. The whole remainder comes from the plus 2. But if I divide by 7, so this one is 79. And I'll call that step 2. We basically just multiplied the two numbers, but added the remainder onto it. But today's lesson is about the third type, really. Type 3. Different remainders. Let me just make a couple of observations first. 13 mod 11 is equal to 2. What if I take that 13 and I add on 1, 2, 3, 4, 5 times 11? And I want to know what is it if I divide by 11, what would the remainder be? So 13 mod 11 is 2. What if I do this giant number, 13 plus 1, 2, 3, 4, 5 times 11, and I mod that by 11? Anyone have a suspicion about what the remainder would have to be? Okay, Lisa, you say 2, and that's right. Why do you think the answer is still 2?
Because if you're dividing by 11, right? Like if you're whatever you're multiplying by 11, that's going to go in evenly. So it's just going to be the same remainder no matter what you're multiplying 11 by.
That's right. So I'm going to say adding a bunch of 11s does not change the remainder. Adding a bunch of 11s does not change. That's going to be a key insight for today's lesson. Here is a funny looking expression. 2 times 2 times 5. Oh, wait. Don't like that. That's for 3 by 3. Hold on. Stuff is flying all over the place here. Okay. Everyone hold on one sec. I'll be back in a second.
Lisa. Hello, Lisa. Can you hear me?
Hey, everyone, I'll be back in 1 second.
Hi, yeah.
Could you please explain what you just said now about this 13 mod 11 equal 2? How did you get the 2, please?
And I think he's taking I think something's going on. We're waiting for him to come back. I don't think he can hear you. Are you asking the professor?
I'm asking Lisa.
Oh, you're asking Lisa. Oh, sorry.
Yeah, it's okay.
So like like so if you're dividing, right, something by 11, right, and the remainder is 2, no matter how many times you multiply any other number times 11, like you're still going to have that remainder of 2 because the number you're multiplying by, like you're making a multiple of 11, right? So if you're adding on the 13, you're going to have that same remainder of 2.
So say that again. You said no matter what?
Yeah, so like he just like randomly chose a number and multiplied it by 11. Like you could put any number there, and whatever you get is a number that's evenly divisible by 11 because you're multiplying times 11, right? So like you could have like 50 times 11 or 7,000 times 11, and like any way that you slice it, like that number is going to be evenly divisible by 11. So then when you're adding the 13 onto that, you just have to take into account that 13 divided by 11, right, is going to always have a remainder of 2. So you're basically like multiplying anything times 11 and then adding on another 11 plus 2 more when you're adding the 13.
Got you.
If that makes sense.
Very, very nice explanation. Yes, when you divide by 11, if you add on 11, so maybe we should take some number. We could all agree that, that 14, when you divide by 11, has remainder 3. But if I add 11, if I add a bunch of 11s to 14, let's say I add 2 times 11 to 14, the remainder, this piece isn't going to affect the remainder, is basically. If you add together something that has remainder 3 with something that has remainder 0, the answer will still have remainder 3. So adding on 11s won't change the remainder when you divide by 11. That works. We can be confident about that. Now, I feel like I want to show you a number. I mean, the number is 157. But I'm going to write that number in a funny way. Don't ask yet, why am I writing it in that way? That is going to come up later, like where does this string of 6 numbers coming from? I'm actually going to throw in more numbers. So write down these 9 numbers. 2 times 1 times 11. It's not 157 anymore. It's 47. Okay. Now I just want you to examine not the 47. Well, actually, I do want to look at the 47. If I do 47 mod 5, I get 2 because it's 45. 9 times 5 is 45, and 47 mod 11. 11 times 4 is 44 is 3. I just want to kind of just throw that out there, that 47 has this remainder. But let's now look at these 9 numbers here. If I told you these 9 numbers, it didn't tell you anything about what it equals. I just said, here's a crazy expression. 2 times 1 times 11 plus 3 times 9 times 5 minus 2 times 5 times 11. And I said, hey, I want to know what this is mod 11. Would I'll just say it this way. If it's mod 11, then I can ignore those two things. Does anyone know why am I allowed to ignore? Why am I allowed to ignore those two orange things I just crossed out? Let's see, like a volunteer, or someone just unmute. You could say, why am I saying you could ignore those two things?
Yeah, because
Yeah, Mohammed. Why am I ignoring those orange highlighted things?
they both be multiplied by 11.
That's right. So on the other hand, if I took the same expression and instead I wanted to do it mod 5, then I could ignore this because it has a 5 in it and this. So it's kind of want to mention that. And in this case, I could actually get the answer because 2 times 11 is 22 and 22 mod 5 is 2. So I could actually answer the question. What I'm getting at is that you could ignore any term, in this case, for the 5 that has a 5 in it. On the other hand, in this one, I could ignore any term. By term, I mean like these are groups in like groups of 3. I could ignore any term that has an 11 in it. 3 times 9 times 5 is kind of a big number. For now, I'm just going to multiply it. And I get 135. And 135 mod 11 it ends up becoming 3, but maybe that took a little more work than I wanted to do. But what I'm getting at now is if you have these expressions, if you ever have an expression, even if it's a giant expression, let's say it's 5 times 3 times 7 plus 2 times 6 times 11 plus 8 times 4 times 11 minus 3 times 1 times 11, and I wanted to do mod 11, I could just ignore any terms that have 11 in it. So I'm just going to say like the 11s don't, the terms with 11s in them don't affect the remainder. That is the insight that's going to be important. And now I'm going to very carefully do the instructive example. This is going to become an algorithm. It's an algorithm that's not that hard to do. It's a little confusing why it works. So I'm going to explain this really, really carefully. It's going to take about 15 minutes to explain. But here is the big instructive example. And I'm going to do something kind of funny. I'm going to prepare for the answer by putting in a bunch of slots and numbers. That's a minus sign. So there are going to be 9 numbers in this answer, and 4 of them are going to be filled in instantly, but the other 3 are not. So if you're wondering, where are these numbers? Oh, shoot. Sorry. I really would prefer to put the 11 there. Okay, so the two key numbers are the 5 and the 11. Right now, you don't worry about the 2 and the 3. We'll deal with those in a minute. This is how we start the process. These 9 numbers are going to turn into the answer to the question, and 4 of the 9 numbers are filled in this way. We have the 5 and the 11 are in 2 places. The 5 is sort of by itself at the end of one of the things. The 11 is by itself at the end of the other. And the 5 and the 11 are together in the third one. It doesn't really matter whether if you had the 5 where the 11 is and the 11 where the 5 is, it wouldn't matter, but I'm just going to do it this way. Okay, so that's what step 1 is. Here comes step number 2. Put the remainder for the dividing by 5, put it in the beginning of the one with the 11. And put the remainder that you want to get for 11, put it with the 5. Now, right now, this is mysterious, like voodoo. You're like, why am I doing this? These numbers are flying all over the place. I am going to explain the logic afterwards, because I feel like first producing the answer is going to be useful to us, and then understanding like, oh, why am I doing that? What's going on here? Now, in this spot right here, you are going to put 11 inverse mod 5. So you head over to your trusty table. 11 inverse mod 5. Where is that trusty table? It's oh no, my trusty table is missing rats. I purposely chose one that I thought was all good, but I don't have the column, I don't have the row there. So instead of heading over to my trusty table, I'll head over to my trusty calculator. Of course, 11 inverse mod 5 is 1, because 11 divided by 5 is remainder 1. So let me come over here. That's because 1 times 11 is equal, 1 times 11 is congruent to 1 mod 5. In this one here, we're going to do the opposite, 5 inverse mod 11. Well, that is on the chart. 5 inverse mod 11 should be 9, because 5 times 9 is 45. 5, yeah, it's 9. Or we just switch the order. 5, 11. It's 9. Now what you do is you calculate this, which is 22, and this, which you use a calculator for, 3 times 9 times 5 is 135. So just to recap, these two numbers are the two remainders that you want to get. These two numbers are the two mod numbers. And these two numbers come from the inverses. So the 4 of the numbers are literally just the 4 numbers here, but just knowing where to put them. And these two numbers came from inverses. Now, I will tell you that 147 is the answer to the question. Watch.
What about the last chunk?
Yeah, that's coming, because 147, I want to get a smaller answer. But if I go to desmos.com and I type hold on, and I type mod 147 comma 5, I do get 2. And if I say mod 147 comma 11, I do get what? Uh-oh. It's not 147, apparently. It's 157. Try that again. It was supposed to be 150. It's 122 plus 135 is 157. Sorry about that. So let me try that again. 157 was 2, and 157 was 3. So that does get me an answer. But it's not the smallest possible answer. So on the side, I'm going to do 157 divided by the product of 5 times 11, which is 3 remainder 47. The 3 goes here, and the remainder goes there. Don't worry, I'm going to do another full example from start to finish, but I just wanted to at least take you through, the steps. And I'm going to come back to this page in a sec, but let me just demonstrate that at least we can see mod 47. 47 mod 5 is 2, and 47 mod 11 is 3. So it did work. I am going to take you through a full second example now and explain about, the different steps. In fact, what was the, where was that question? Where, whoa, all the way back? No, not that one. I want one with 2. Where is it? Okay. This question. 8, 11, 5, 17. Okay, here we go. I'm going to take you through the process. I am going to put the 8 here. Okay, I hope you don't mind. I'm going to actually start with just 9 slots. So I can just plus 1, 2, 3, minus 1, 2, 3. 17. Actually, I like that. 8, 17. Huh. Just take this number first, then put that number. Then take the 5 and put it here, and put the 11 there. And then put both the 11 and the 17. I know you might be thinking, why are we doing this? This is like so crazy. Numbers are flying all over the place. I promise I'm going to explain the method to the madness. But even if you don't understand the methods of the madness, you certainly can take these four numbers and put the first number here and the second remainder here, and just put the number with the opposite mod, put the remainder, like if 8's here, put it with the 17, and put the 11, put the 5 with the 11. Now in this spot, you're going to do the inverse of 17 mod 11. And that's not going to be on our chart. So we're going to instead come over here and say 17, 11. And we get 2. And that's what goes right here. And over here, I'm just going to do the opposite. 11 inverse mod 17, which I'll come over here. And it ends up being 14. Now I get my calculator out and do 8 times 2 times 17 and get 272. And 5 times 14 times 11 and get 770. And add those together. And get 1042. And just for a sanity check, I'll come over here and say mod 1042 mod 11 does come out to be 8. And mod 1042 comma 17 does come out to be 5, like I hoped. But I want to cut this number down to size. So on the side, I do 1042 divided by 11 times 17. And I get 5.57. The 5 goes here. And the remainder, which I could be sneaky since I'm using a calculator anyway. But you know what? I won't be that sneaky. I'll do 1042 minus 5 times 11 times 17 and get remainder 107. And 107 is the answer to the question. If you don't believe it, mod 107 comma 11 does come out to be 8. Mod 107 comma 17 does come out to be 5.
How did we get 14 for this 5th slot?
This one, right? Yes. That 14 I got by doing this. 11 inverse mod 17. Basically, it wasn't on our chart because our chart didn't go up to 17.
Mm-hmm.
But if it did, that's what it would be. Basically, 11 times 14 divided by 17 will be remainder 1. But it came from this.
Okay.
Now, I want to show you now, before I'm going to have you practice and do an example with groups. But let me grab this thing for a second. Copy, new page. I want to give you a little bit of insight as to how this works, why this works. So check it out. And I think you'll like this because it's all mysterious now. If we take this thing, let me make another copy of it also. Actually, I want to make 2 copies of this. Oops. Oh no, undo. Well, that didn't go well. Sorry, I got to come back and do this again. What numbers in here? I lost some numbers. They were supposed to be 5, 14, 11.
And then the 5 came from the amount of times that
It was
11
that
times.
5 came from that 5. This one came from, it was the remainder. It was that remainder. So the first two numbers are the remainders. This and this are the remainders.
Yeah, no, I was talking about the last 5.
Oh, the
Is
last
11 times
5 was
17 goes
because
into,
when I divided, 1042 was so big, I
yeah,
divided it by 11 times 17, and it went
okay,
in 5 times.
okay.
Now I want you to check this out. This big, ugly expression, if I mod it by 11, what happens is that this term, I'll use the same color as before, doesn't contribute to the remainder because it's got an 11 in it. And neither does that term because those the groups of 3 that have 11s in them don't affect the remainder. So the entire remainder is based on this thing. Now you might say, okay, I don't feel like I could multiply 8 times 2 times 17 and divide by 11, but I'm not going to because I chose this 2 for a reason. What should 2 times 17 mod 11 be? Anyone know? Just forget about the 8 for a second. What if the 8 wasn't there? What should 2 times 17 be? By the way, why was the 2 chosen?
It was the inverse.
It's the inverse. So 2 times 17, it actually becomes 34, which becomes 1. And I'm not surprised that this became 1 because it was chosen to become 1, which means the 8 is the answer. Because 2 times the 2 was chosen, so the 2 and 17, 2 times 17 is 34, 34 mod 11 is 1. I chose that 2 to force the 2 times 17 to become 1. And that's why the answer is 8 for this one. But if instead I take the same 9 things and instead I do mod 17, then this term doesn't matter because it has a 17 in it. And this term doesn't matter because it has a 17 in it. And these 2 things don't matter. Someone want to tell me why don't the 14 and 11 matter in calculating out?
Remainder 1.
It's remainder 1 when I divide by 17 because I purposely chose 14 for that reason. So that's why the answer is 5. And that is why these weird expressions that I showed you, I'm going to write out the expression again. 8, 2, 17 plus 5, 14, 11 minus 5, 11, 17. This 2 was chosen so that when I divide by 11, these don't matter and these don't matter because they become 1 because I chose 2 for specifically that reason. On the other hand, when I divide by 17, these don't matter and these 2 don't matter either because they turn into 1. So it's really ingenious.
So the answers are 8 and 5, but what does that mean?
Oh, it means this number, which is 47, is the answer to the question. Because that big string of numbers was 47 when you actually multiply it out and subtract and all. So it's saying that 47 divided by 11 is going to be 47 mod 11 is 8, and 47 mod 17 is 5.
Oh, we were
So
like,
I created a number that has all the properties. Now, I'm going to tell you something. You don't really have to understand all the ins and outs of why this works. That's why I'm going to put you into groups right now with a single question, which is to try to do this process. And I'm going to purposely use numbers that you could use the chart for if you want.
So
Yes?
on the previous one, like the,
Yes.
after all that math,
Yes.
sorry, what was the answer? X was 107? Is that?
No, I'm sorry. Did I say 107? Did I say 47 here? I meant 107.
Okay.
Yes,
Yeah,
yes, that
I'm
was
not
the
in-
answer.
My brain-
107 was actually calculating this thing out.
Okay.
This last term, it serves to make an answer that's smaller that won't have a different remainder when I divide by 11 or 17, because it has an 11 and a 17 in it. Let's have you go into groups, because I think if you could just get the answer to this question, you know, with the 9 things, that's all you would need to do on the final. You don't have to understand why it works, but of course, it's important that I like give
And to
some
confirm, in the
attempt.
last one that we did, the answer to the 9 things was 107.
That's right,
Okay.
because it was 1042.
Yep.
But then when I divided by 11 times, I got 50. I got 5 remainder 107.
Yeah.
So the answer was the remainder after I divided this number by whatever, by 187.
Okay. Thank you.
For a final, this will absolutely be a final exam question like this. If you could put the 9 numbers in, I'm happy about that. So I'm going to put you into groups for 10 minutes to work on this one question. Again, even if you're totally confused, you just know, okay, I don't know what I'm doing, but the first 4 numbers, I could fill in 5 boxes this way, and the other 3 come from doing this. I'll be totally happy. So into groups you go. Where is this thing? Breakout rooms. So try to get the numerical answer to the question. Fill in the 9 numbers.
Am I in the breakout room or it's just you and me? Professor, can you hear me?
Yes, yes. Which room were you in?
I was with Genoa and Tammy.
Okay, I'm moving you to that room right now. Okay, did any of the groups get 135 as their answer?
Yes.
Yes.
So as you can see here, I have the work done. Why, when I was doing this, did I get annoyed from an instructional purpose? Anyone know why I said, oh, that was unfortunate as far as instructional purpose goes?
You told us that we could use the chart.
Yeah, no, you can use the chart, but I still got annoyed.
The mods were the same. Or I mean,
Yeah,
well, yeah, like
that was annoying because you might be confused which one should be which. So sorry about that, but that's just what happened. 13 times 6 is 78. 78 divided by 11 is 7 remainder 1. 6 times 11 is 66. 13 times 5 is 65. So that was just total coincidence. Usually those will be two different numbers. Now, if you can do this on the homework and the test, I don't mind if you're not like, if you're confused, like, how did that work? Why did that work? It's okay. Because the test question would be like this. It helps if you understand why it works. It might like let's say you got confused. You're like, oh, I'm not sure which one to put here. Well, the reason it's got to be 13 inverse mod 11 is so that this thing cancels out so that we get this remainder when I divide by 11. On the other hand, I know this needs to be 11 inverse mod 13 because if it is, then these two things together become a 1, which makes the 5 come out when I divide by 13. You know, so like knowing why it works might help me not get these two things backwards. Of course, in this case, even if you got them backwards, you still get the right answer because they're both 6. I'm going to stop the recording.
Professor, I have a question.
Yes.
So from the part where you put x equal to 34 plus 39330, that gives
Yeah,
564 I get. But everything after that, I'm confused.
Oh, okay. Because 564 is actually an answer to the question. But I want a smaller answer. I think I would say I want x to be between 0.
564 is not the answer, right?
Well, 564 does satisfy this equation, but I think I would say on the question that it's got to be less than 143. So this extra step on the side enables me to get this minus thing. See, this minus makes a smaller answer, but it doesn't mess up the remainders because 11 times 13 is a remainder 0 when you divide by 11 or 13. So that's where that extra thing came from. So 564 is almost full credit, but to finish it off, divide 564 by the product of the two mods, which is 143. 564 divided by 143 is 3 remainder 135, and 135 is the answer. If you want, you don't have to write this if you don't want.
Wait, how did you get 145, 147?
564 divided by 143.
Where did you get 143? How did you get 143?
11 times 13.
Okay.
So as long as you take your answer, this answer at the end, and divide it by the product of the two mod numbers and take the remainder, you don't actually have to have this here. I like it there because I like it there. But if you get the 564 and you know what to do with that to divide by 11 times 13 and take the remainder, that's totally fine. I just like to see the answer sometimes as one big string, which includes the adjustment factor at the end to shrink it, to shrink it down to size. Yeah, I'm going to stop the recording. Hold on. I'm still here, though. I just want to stop